Welcome to the video lecture of Newton's third law. We'll be looking at Newton's third law, which states for every action force there's an equal and opposite reaction. We'll also be applying this law to systems such as two people pushing off each other, shooting a gun, the recoil effect, so on and so forth. Let's get started. So there you see the definition on the top of that screen. To every action there is always an equal and opposite reaction, or the forces of the two bodies on each other are always equal and always directed in opposite directions. So forces in nature always exist in pairs. That's really what he's trying to get across here with when he was discovering this law or writing it down, and that these pairs are typically in opposite directions of one another, and depending on friction, no friction, they would be equal to one another. Okay, so let's look at the first example, because really understanding Newton's third law is the best way is looking at two examples. So you have two people, a girl and a woman on ice skates, so a very low friction environment. So typically we would say this is friction free. You have a girl on one side and a woman on the other side, and you see there at the underneath their feet that the woman is pushing in the negative direction, and the girl is in the positive direction. So because in this system they are not moving at this point in this picture, their center of mass is right in the middle. So right there is their center of mass. Okay, and so the net force on this system is zero, as you can see down here at the bottom. It says the net force on the girl/woman system is zero. So therefore they're not moving, or they're not moving in a constant velocity, no acceleration, no force. All right. So if these two women push off on each other, they're going to feel an equal and opposite force on one another, no matter who pushes harder on one another. Okay, they're always going to have they're going to feel an opposite force of the net force in the system. Okay, so if the girl pushes off with 10 newtons and the woman pushes off with 30 or 20 newtons, the girl's going to feel an equal opposite pressure to the net system. So 20 minus 10, she's going to feel a negative 10 newtons, along with the woman also feeling the opposite, which is going to be 10 newtons. Okay. We can look at NASA. I apologize for the blurriness of this picture. Google, good stuff. But we can talk about NASA and the fuel rockets, and how the fuel exhaust is being pushed out of the back end of the rocket, being ignited, and the propulsion of all those atoms being thrown backwards is pushing that rocket up into space. So you can see with that diagram, as the things are leaving the back, it is pushing the rocket forward. Okay, and this is why maneuvering in space is so difficult, because there's no friction to slow you down. So you have to have a really balancing and understanding of Newton's third law. All right, so let's look at gravity. This is harder to see because the Earth is so big, but actually every time you throw an object into the air, we say the force of gravity pulls the stone down, which is true, but the stone also produces a force here because it has its own gravity. It's just so much smaller that it's insignificant in the total system. But however, it does pull on the Earth, so it actually brings the Earth towards it. It's just that the amount that the Earth moves towards that rock is so small that it's negligible in the actual mathematics. So we actually, when we were learning this, I just ignored that. But now that we're finally in Newton's third law, we can actually discuss how the mass of these two objects actually generate their own gravity, and those two pulls actually pull on each other. It just depends on which one has the bigger mass. And we'll talk about that in class and look at that equation, how that plays out. Okay, so I told you about the gun recoil. So if I shoot a gun, why do you fly backwards when the gun is shot? So this is what they call the recoil effect. And so the bigger the bullet, the more the recoil. And so engineers have been working for centuries and centuries on mastering this gun and recoil. Can I have a bigger explosion and minimal recoil? And that's really what they're researching, trying to put things in the way to absorb that reaction force that in a gun's case we call recoil. So a lot of times you'll hear this reaction force called a recoiled force because it's opposite of the initial force applied. Okay, so let's look at an example real quick. A man of mass 75 kilograms and a woman of mass 55 kilograms stand facing each other on an ice rink, both wearing ice skates. The woman pushes the man with a horizontal force of 85 newtons in the positive x direction, assuming the ice is frictionless. What is the man's acceleration? What is the reaction force or the recoil force acting on the woman? And calculate the woman's acceleration. Alright, so let's get our picture here, let's get it drawn, let's make our list, and let's really dive into this problem. Alright, so I'm going to set up my problem here. So let's make our list of the information real quick so we can make sure we do our math correctly. And so I have my mass 1, which is going to be my man, and he's going to be 75 kilograms. Okay. And then I have my mass 2, keep them separate here, make another column, which is she's going to be 55 kilograms. Oops, sorry about that. All right, and see, she has a force that she's applying of 85 newtons in the positive. I apologize for that, 85, not 8 newtons. Okay. So what is he experiencing? He is experiencing a equal and opposite of the total, right? So the net force here is 85 newtons, okay, pushing against him. So he's actually experiencing a positive 85 newtons force on him. And she, in answer question 2, what is her reaction force? So here, she is experiencing, let's write it red so that way we can make sure we distinguish it. So her reaction force, I'm going to put 2R, is actually going to be a negative 85 newtons. Because she's applying it, she's going to feel that. So there's question number 2's answer. Okay. Let's go back to blue here. And ask us what is the acceleration of the man. So what is A1's acceleration? And then it asked me to find the acceleration 2 of the woman. Now that I have that answered. Okay, so F equals ma, and we can use our equation here. So let's see, F equals ma. Put a better A there. All right. So here we go. All right. So the acceleration of the man is going to be 1.13 meters per second squared, and the woman is going to be negative 1.54 meters per second squared, and her reaction force is negative 85 newtons. All right, and I have 3 significant figures given to me in the problem, so as long as my answers are in 3 significant figures, so I have 1.13, there's 3, 1.54, and my answer here, 85, should be 85.0 newtons to get sig figs in there. All right, negative. So that should be my overall answer. All right, final concept real quick is action-reaction force pair. So when an object exerts a force on the second object exerts an equal and opposite force back on the first object. So let's go back to the man. The man was applying a negative 85 newtons, but he felt a positive 85 newtons. All right, so that's kind of where the trickiness is. He applied the opposite of what the girl applied, but he felt the girl's force, if that kind of makes sense, because it was equal and opposite. And the girl felt opposite of what she was pushing, which is opposite of the man, or what the man was pushing. Now it's different from the first girl because there was the forces were different, so you had to actually figure out what the net force was between them before you could say which felt what. All right, So the last statement there, equal and opposite force does not mean zero acceleration, as we just found out with the bodies, because it's all determined on mass. All right, if the two objects were the same mass, then acceleration for the two objects would be the same. But if they're not the same mass, as we just saw with the ice skaters, the man and woman, the accelerations are not the same. So it's a little tricky there, but I think everyone will do just fine. All right, good luck.